All right, if you're a Python developer, you know this feeling, right? You've got this incredible, expressive language, this huge ecosystem, but every now and then you just hit a wall, a performance wall. Today, we're going to talk about a future where breaking through that wall is way, way easier than you ever thought possible. So picture this. Your app is running. It's beautiful. The logic is sound. But it's just slow. You fire up the profiler, and it points to one single, solitary function that's causing all the trouble. Now, what if you could fix that, get a massive speed up without a painful week-long rewrite? What if it was just one command?
I mean, this is such a classic scenario, isn't it? You run the profiler and bam, there it is. One hot function, a single bottleneck just sitting there eating up 80% of your CPU time. And you just know it would be faster in C++. But the thought of all that integration work is, well, it's just exhausting.
And that leads you to the usual choices. And let's be honest, none of them are great. You could rewrite it in C++, sure, but then you have to spend ages writing all this tedious boilerplate or glue code just to stitch the two languages together. It's so brittle and error-prone that a lot of the time, the easiest path is to just not bother.
Okay, so before we get to the solution, we really need to understand the problem. Why exactly is C++ so much faster for these kinds of heavy lifting operations? It all comes down to what's happening under the hood when each language looks at what seems to be the exact same instruction.
Let's look at a super simple example, a dot product function. You can see the Python and C++ versions. They look almost identical, but here's the kicker. Python is dynamically typed. It has to figure out what X and Y are when the code is actually running. C++, on the other hand, is statically typed. It knows what everything is before the program even starts. And that single difference is the entire source of this massive speed gap.
And this is where it gets crazy. The real story here is the overhead. When your Python code calls a C++ function, it's not just a simple jump. First, it has to look up the method. Then it has to wrap up all the arguments into these generic Python objects. Then it's got to do type checking, manage the GIL, and only then does it actually call the C++ code. The math part is lightning fast, but it's buried under all these layers of prep work. And C++, what's its journey look like? Well, the compiler boils it all down to about 9 machine instructions. That's it. No runtime lookups, no type checks, no allocating new objects. It just loads the numbers, does the math, and it's done. That efficiency gap is the whole reason we want to do this in the first place. So you do it. You build the bridge to C++. You run your benchmark and, well, you might be a little underwhelmed. Let's dig into why your first instinct for testing performance might be totally, completely misleading.
So here's what that first kind of naive benchmark looks like. We just call that dot function a million times inside a Python loop. And yeah, the C++ version is faster, almost 3 times faster. I mean, it's not bad, but it's not the earth-shattering 100x speedup we were hoping for, right? So what's going on?
This is what I call the Ferrari fallacy. It's like you've got this incredible sports car, but you're testing it by seeing how fast it can start and stop at a million red lights in a row. You're not measuring its top speed out on the open road. You're just measuring the overhead of hitting the brakes and the accelerator over and over again. You're measuring the toll, not the journey.
And that brings us to the real secret. The key isn't to replace one tiny function call. It's to identify the entire performance-critical loop, the whole chunk of work, and move that into C++. You pay that border-crossing toll between Python and C++ exactly once. And when you do it the right way, the results are, well, they're not just good, they're dramatic. This is the kind of number we were looking for.
Okay, this is the real benchmark. Instead of a million tiny trips across the border, we move the whole loop into C++ and make one single call. The original Python loop took about 1/4 of a second. The new C++ version, just 4/1000ths of a second. That's our 67 times speedup. Now we're talking. That is what surgical optimization is all about.
Okay, that is incredible. But wait a minute, we kind of skipped over the hard part, didn't we? The whole reason people don't do this is because of that painful, tedious glue code. So how on earth did we connect our C++ to Python with just one command? Man, this slide right here says it all. On the left, that's the old way. You have to manually, line by line, list out every single function, every variable, every little thing you want to expose to Python. It's a headache, and it breaks all the time. And on the right, that's the new way. You write your C++, you run one command, and you're done. So what's the magic trick here?
It's all thanks to a game-changing new feature coming in C++26 called static reflection. Think of it like this. It finally gives the C++ compiler the ability to talk about the code it's compiling. It lets a program understand its own structure, but, and this is the critical part, it does this at compile time, so there is zero performance penalty when you actually run the code.
So let's break down how this actually works. It's pretty brilliant. A tool uses this new reflection operator to basically go up to the compiler and say, hey, tell me everything you know about this piece of C++ code. And for the first time ever, the compiler can answer. It hands over a perfect blueprint, all the functions, all the variables, their names, their types. The tool then just takes that blueprint and automatically generates all that perfect binding code for you. The compiler does all the heavy lifting. You see how this just completely changes the game, right? It fundamentally alters the whole cost-benefit analysis of optimizing Python code. We are looking at a future where you can truly, finally, have the best of both worlds, with none of the usual friction.
This is basically the 80-20 rule, the Pareto principle, applied to your code. You keep the vast majority, say 80% of your application, in Python. You get to leverage its amazing readability and that incredible ecosystem. Then, you surgically identify that tiny 20% that's the real performance bottleneck, and you rewrite just that part in C++. And with this new frictionless binding, you get Python's awesome ergonomics and C++'s raw, close-to-the-metal speed.
So I want to leave you with this question. The next time you're staring at a profiler and you see that one slow function, the question is no longer, is it worth the hassle to optimize this? That friction is just melting away. So the real question isn't, can I make this faster anymore? It's, if optimization takes 5 minutes, what am I going to build next?